Hi everybody, this is 7.2.2, Confidence Intervals, Lesson 2. First, we're going to do a review of the 95% confidence interval. The sampling distribution of sample proportions includes all sample proportions from random samples of a fixed size n. When n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10, this distribution is approximately normal. The standard error in the sampling distribution of sample proportions uses the population proportion p. So the standard error is obtained by using this formula. It's the square root of p times 1 minus p divided by n. For a 95% confidence interval, the margin of error is 1.96 standard errors. Because the population proportion p is unknown, we estimate the standard error using p hat instead. So recall from the last lesson that because we don't know p, we use p hat, the sample proportion, instead of the proportion to calculate the margin of error. And that's this formula right here. When the criteria for approximate normality are satisfied, the true error in a sample proportion is less than e for 95% of sample proportions. The 95% confidence interval for a population proportion is computed using this formula, p hat plus or minus e. We can express the confidence interval in interval notation as, so this is how you do it, you put it in parentheses, and let me highlight this so you guys know what I'm talking about. You put this in parentheses, and on the left you put the smaller number, p hat minus e, and on the right you put the bigger number, which is p hat plus e. This notation lists the lower and upper limits of the interval. We are 95% confident that the unknown population proportion is between p hat minus e and p hat plus e. The criteria for approximate normality. The population proportion p is unknown. Otherwise, we wouldn't need a confidence interval, right? So we can't calculate n times p and n times 1 minus p exactly. So instead of checking the expected number of successes and failures, we check the actual number of successes and failures in the random sample. If we are given the proportion of successes in the random sample p hat, we can calculate the actual number of successes and failures by n times p hat and n times 1 minus p hat. Okay, so this is if you're given the p hat. If you're not given the p hat, you could just calculate p hat yourself, right? Keywords in the updated criteria above are random sample. Researchers should not try to choose a sample so that it has the right number of successes and failures. They must continue random sampling until at least 10 successes and 10 failures occur by chance. This is extremely important, okay? The sample needs to be random. Needs to be random. Okay. So let's go ahead and go to the next part here. So try these. This is going to be a problem that we can work out. According to a poll commissioned by the website creditcards.com in March 2015, 36% of U.S. adults aged 18 to 29 have never had a credit card. In a news article about the survey, a reporter noted that the results were based on a random sample of 142 young people. So first, are the criteria for approximate normality satisfied? Okay, so we need to check if the number of, let me move to a pencil here. We need to check that the number of successes and the number of failures are at least 10, right? Now, we do not know that the problem doesn't tell us in that sample how many actual adults have never had a credit card, but they tell us that 36% of them. So what we need to do with that is we need to multiply n times p hat, and here we need to multiply n times 1 minus p hat. Because they gave us p hat, right? 36%. So it's going to be 142 times 0.36, and this is going to be 142 times 1 minus 0.36. This is an easy enough calculation. So if I multiply 142 times 0.36 in my calculator, sorry about that, I actually end up with 51.12. And if I do 142 times 1 minus 0.36, I end up with 90.88. Both of these are bigger than 10, so this means the criteria for approximate normality are satisfied. Okay? So let's go to the next part. Find the margin of error for a 95% confidence interval. Okay, so we need to use our formula. We know that for a 95% confidence interval, the formula is 1.96 times the square root of p hat times 1 minus p hat divided by the sample size n. So this is 1.96 times the square root of, it's going to be 0.36 times 1 minus 0.36 divided by 140. So I'm going to do this part on my calculator. I wanted to demonstrate this. So I have 1.96, so 1.96 times second square root, and then under the square root I have 0.36 times parentheses 1 minus 0.36 close parentheses divided by 142. So if I hit enter on that, I get 0.07895, or if I round that to 3 decimal places, I get 0.079. Okay, so that's what I'm going to put there, 0.079. Okay, so coming back here, this is equal to 0.079. So this is the margin of error. So what does this margin of error mean? So it says interpret the margin of error. So this is saying 95% of all so 95% of all samples of size 142 will give us a sample proportion that is within 0.079 of the population proportion. Remember, the population proportion is the one that we care about, but we're never going to know what it is exactly. Okay? So now, what is the 95% confidence interval? Remember, we have to do p hat minus e, and then we have to do p hat plus e. So what is p hat minus e? P hat was given, remember, that was 0.36. So this is going to be 0.36 minus 0.079. And the other one is 0.36 plus 0.079. So if I do the subtraction first, I get 0.281. And if I do the addition, I get 0.439. So what would the confidence interval be? Now I want to be careful and specify this is the 95% confidence interval. It goes from 0.281 and it goes until 0.439. Okay. Or if I wanted to, I could give it with 2 decimal places. So if I want to do it with 2 decimal places, I can do it 0.28 until 0.44. Right? This is just me rounding to 2 decimal places. Okay. Now every single one of these confidence interval problems is going to ask us to write a sentence to interpret your confidence interval in context. Okay, so how do we interpret this? Here's how we say this. We are 95% confident that we don't just say that the population proportion, okay? We want to do it with the context of the problem. And remember, we're talking about US adults age 18 to 29 that have never had a credit card. Okay, so we want to say we are 95% confident that the proportion of all US adults aged, what was it, 18 to 29. 18 to 29. So we are 95% confident that the proportion of all US adults age 18 to 29 that have never had a credit card is between 0.28 and 0.44. I could have written 0.281 and 0.439. I just chose to use 2 decimal places this time. Okay, so this is how we want you to write the sentence in context, okay? You need to understand what it is that you are finding when you find this confidence interval. You're finding an interval that you're pretty sure that the real answer sits inside of, okay? Okay, let's look at part F here. It says, based on the confidence interval, is it reasonable to say that the majority of US adults aged 18 to 29 have never had a credit card? What does majority mean? Majority means more than half. Is it reasonable to say that more than half have never had a credit card? Well, not really, because look at the confidence interval. The confidence interval goes from basically 28% to 44%. So it's not reasonable to say that more than half. That's definitely less than half, no matter which number you pick in there, right? So, no, it is not reasonable, since the entire interval is less than 0.50, right? Or less than half. Okay, so that's not a reasonable answer. Now, if they had said 40%, that's reasonable, right? Because 0.40 is inside of there. Or if they had said a third of all adults, that's reasonable too, right? Because A third is 0.33. Okay, but you need to make sure that claims that are made fit the evidence, or we reject them. We say that it's not reasonable. Okay, so let's keep going here. Next steps. To compute a margin of error, we determine the number of standard errors from the mean needed to contain a certain percentage of sample proportions. This number of standard errors is called a critical value. A number of standard errors or deviations from the mean is by definition a z-score. Critical values are denoted z sub c and can be found by examining the standard normal distribution. We have seen that the number of standard errors for a 95% confidence interval is 1.96. This tells us that the z critical value that corresponds to 95% confidence is zc equals 1.96. So what we're about to learn basically is that the only thing that made 1.96 special was that was the critical number that we use for a 95% confidence interval. But if you want a different level of confidence, then that number is going to change. Okay? So let's go on here. It says for a 90% confidence interval, we find the critical z-score where 90% of the distribution is contained between negative zc and zc. The area between these values is smaller, 0.90 instead of 0.95. Does this make zc smaller or larger? Well, I want you guys to visualize this, okay? So what we're saying is that 1.96 standard deviations gives us 95% of that curve. But if we wanted less of that curve, are we going to go more or less standard deviations away? The answer is less, okay? So ZC would be smaller. Right? In other words, we would have to shrink this. We would have to shrink this down if we wanted to get 90% under the curve instead of 95%, right? Because if we squeeze these closer together, this guy is going to change. So let me show you guys in this next picture exactly what we're talking about. It says below is a plot of the standard normal distribution with mean equals 0, standard deviation equal 1. It says use technology or tables to find the value of the z-score that has 5% area to its left and the value of the z-score that has 5% area to its right. Okay. So we don't have a table or anything like that with us, so I will just go ahead and tell you guys the z-score, okay? So the critical z value that we would use is actually 1.645. So in other words, this guy would be 1.645 standard deviations to the right, and this would be 1.645 standard deviations to the left. Okay. Which makes sense, right? 1.9 something gave us 95%, but of course, if we only go out 1.645 standard deviations, that is going to give us less under the curve. Since 90% of the area under the standard normal curve is between negative 1.645 and positive 1.645, the critical value for a 90% confidence interval is ZC equals 1.645. Other levels of confidence have their own critical values, each capturing the corresponding percentages under the standard normal distribution. The table below gives the most common critical values. So I want you to look at this table here. This is a table. This table right here gives us the 3 most common critical values that you're going to see in this class. And in fact, on an exam, these are the only ones that you'll ever see, okay? If we want 90% confidence level, then you're going to use 1.645. If you want a 95% confidence 95% confidence level, you're going to use 1.960 or 1.96, right? Same thing. And if you want 99% confidence, you're going to use a critical z-value of 2.576. Note, you do not need to memorize those numbers. It will be given to you on an exam, okay? So we're going to illustrate this graphically. So the figure below graphically depicts these critical values and the areas captured between each critical value. So you could see here that if you want 90% confidence, it's between negative 1.645 and 1.645. If you want 95% confidence, you've got to go back negative 1.96 to positive 1.96. And then if you want 99% confidence, you've got to go left and right 2.576. Okay. We've seen that different levels of confidence yield margins of errors that require different critical values. For a 95% confidence interval, the number of standard errors in a margin of error is 1.96. The margin of error is 1.96 times that square root, right? This is what we did in the last section. Now, if we wish to compute intervals with different levels of confidence, what's the formula going to become? All we need to do is use the critical value from above. So you get the one that you need from this table, and then you use it in this formula. Right? So this formula that you had before, that's really the critical z-value, but you were just using 1.96 because the problem was asking you for 95% confidence. However, if it asks you for 90 or 99, you're going to use one of the other two values. So this is the true formula, okay? This is the one that you're going to use for the margin of error, okay? You take the critical z-value that we care about, and we multiply it by that square root. Once the level of confidence and margin of error are known, we can compute a confidence interval. However, remember that another sample with a different sample proportion would give a different confidence interval. In fact, we could calculate many different confidence intervals using different samples. Remember we did that with the blue M&Ms last time? Remember that every sample gives you a different confidence interval. Most of these intervals would contain the population proportion, but some would not. The level of confidence is the proportion of such intervals that actually contain the population proportion. Right? So in other words, if you do a 95% confidence intervals, that means 95% of the time you're going to capture the real answer. When we interpret a given confidence interval, we can say that the level of confidence is the proportion of similarly constructed intervals that contain the population proportion, or that it describes how confident we are that the population proportion is in the interval. This is usually how I say it. When I write the answer in context, I say we are 95% confident that this thing contains the real answer. And so that's how all of the answers are going to go. Okay, so let's summarize everything that we've talked about in the last few sections, okay? So these are the steps for computing a confidence interval with a population proportion. Step 1, verify that the random sample has at least 10 successes and 10 failures. Step 2, determine the critical value, ZC, that corresponds to the chosen level of confidence. And again, the way you're going to do that is by using this table, okay? Step 3, compute the margin of error. You're going to take the critical z-value and you're going to multiply it by that square root, and that's going to give you the margin of error. Step 4, you're going to compute the confidence interval. Okay, the way you represent it is by p hat plus or minus e. Or if you want to do it as an interval, it's going to be p hat minus e, comma, p hat plus e. The interval represents all values between p hat minus e and p hat plus e. Step 5. Interpret the confidence interval in context. The level of confidence is the proportion of similarly constructed intervals that contain the population proportion p. Now, usually you don't have to write all that, but we also say, the second sentence is what I usually prefer. We say it's how confident we are that a particular interval contains the population proportion. Okay, so let's go ahead and do another example. Imagine that we have conducted a survey to learn what college students think about aliens. In a random sample of 758 college students, 159 reported that they believed that aliens have been watching and monitoring Earth for many years. Use this information to construct and interpret a 99% confidence interval for the true proportion of all college students who believe aliens have been monitoring Earth for many years. Make sure to follow all the steps. Okay, guys, so we're going to practice using all of these steps to do a brand new problem. Okay, so first, we have to write it all in this little group here. So let's go ahead and do that. So first thing we have to do is we have to verify normality. So it said 159 reported that they believe that aliens have been watching. And remember, we're talking about college students who believe in aliens, and that is considered a success in this case. So let's go ahead and check normality. So first, the number of successes is 159. The number of failures. So how do you find the number of failures? We're going to do 758 minus 159, and we end up with 599. And both of these guys, so both are at least 10. So normality holds. Okay. Step 2, let's find p hat, right? Well, let me go above and make sure I'm saying it in the right order. It doesn't tell us to do that next, but we are going to need to do that for step 3. Let's go ahead and figure out what p hat is. So p hat is equal to, there were 159 students that agreed or that believed in aliens out of the 758 students that they surveyed. So what's that proportion? Let's go ahead and do 159 divided by 758, and I get 0.21 if I round it, okay? 0.21. Next, we want the critical z-score. What critical z-score do we use? Well, we're talking about a 99% confidence interval, right? 99% confidence interval. The problem will always tell you what level of confidence they want us to use. So I'm going to go back to our table here. 99% confidence is 2.576. That's what we're going to use. 2.576. 2.576. Next, I want to do the margin of error. I know that that's equal to 2.576 times the square root of p hat times 1 minus p hat divided by, the sample size is 758. Okay. So let's demonstrate doing this on our calculator. So I'm going to do 2.576 times second square root. It's going to be 0.21, open parentheses, 1 minus 0.21, close parentheses, divided by 758. When I hit enter, I get 0.038 as my margin of error. So as we saw with the calculator, we got 0.038. So I'm going to go ahead and write that down. This is 0.038. Okay. Once you do that, you get your confidence interval, right? So if you do p hat minus e, you get 0.21 minus 0.038, which is, so if I do this in my calculator, 0.21 minus 0.038, you get 0.172. And if you do p hat plus e, you get 0.21 plus 0.038, I get 0.248. So this is our confidence interval, is from 0.172 to 0.248. Okay, so this is our confidence interval. However, we need to write it as a sentence. Okay, so how would we write this? So I would say, we are 99% confident that the proportion of college students who believe aliens have been watching and monitoring Earth for many years is between 0.172 and 0.248. So the way I wrote this sentence right here is exactly how we want to see answers on an exam or homework or something like that, okay? We are 99% confident that the proportion of college students who believe aliens have been watching and monitoring Earth for many years is between 0.172 and 0.248. Sample size, confidence level, and error. The margin of error is influenced by sample size. Part A. If we increase the sample size, will the margin of error increase or decrease? Explain your answer. Well, I want you guys to recall the formula for the margin of error, right? The margin of error looks like this, doesn't it? It looks like this, and then you have to multiply it by the critical z-score. Okay, we usually have that in front. It doesn't really matter where you put it. Now, what this is saying is if we make n bigger, what will happen to the margin of error? Well, what happens when you take a fraction and you make the bottom number bigger? Right? Because if you notice here by looking at this, the sample size is on the bottom, isn't it? So if we increase a number that's on the bottom of a fraction, it actually makes the number smaller. Okay? So what this means is that the margin of error will decrease. So this means the margin of error decreases if we increase the sample size. By the way, this is a good thing, right? We want the margin of error to be as small as possible because that makes our estimation better and better, right? It means that we can get a really tight fit as to what the actual population proportion is, right? Suppose the sample size from question 4 is increased to 1600, but that the sample proportion remains at p hat equals 0.21. What is the new margin of error? And is the new margin of error greater than, less than, or equal to the margin of error that we computed in question 4? Okay, well, we're going to do the exact same calculation that we did earlier. Okay, except, let's take a look at it really quick. The margin of error that we did before is right over here, right? This was our calculation. And so what we're going to do is we're going to do that same thing, except we're going to replace the 758 on the bottom, which is the sample size. We're going to replace that with what the problem says. So I believe it's, there you go, 1600. So let's see what happens to the margin of error. So I'm going to write 2.576 times the square root of 0.21, 1 minus 0.21, and then divided by 1600. Okay, so I'm going to put that in my calculator. And just to save time, I'm just going to do it. Times the square root of 0.21 times 1 minus 0.21, and then divided by 1600. What I got is 0.026. Okay, so this is the new margin of error. So if we increase the sample size, we got this. And do you guys remember what it was before? Before it was 0.038. So what happened? It got smaller, right? This is less than the margin of error we got before. Okay, so we can see that the margin of error actually gets smaller as we increase the sample size. Okay. If we increase the size of the sample, does the confidence interval get wider or narrower? Explain your answer. Well, think about what's going on, right? When you have a margin of error, if this is p hat, and you've got your confidence interval here, then remember, this is the margin of error when you add it to E, and then this is what you get when you subtract the margin of error, right? So of course, if you make E smaller, then the confidence interval is going to get narrower, isn't it, right? Because you're adding and subtracting a smaller number. So the confidence interval gets narrower as the sample size increases. Let's look at number 6 now. The level of confidence influences the margin of error as well. Suppose we maintain a constant sample size but change the margin of error by adjusting the level of confidence. Does a smaller level of confidence make you more or less confident that the population proportion will be captured within a confidence interval? So think about this, right? Smaller level of confidence, of course, is going to make you less confident, right? I mean, that's like right in the name, isn't it? Smaller level of confidence makes us less confident that the population proportion is captured within the confidence interval. So this is bad, right? We don't want a smaller level of confidence, okay? So let's keep going here. Suppose the confidence level from question 4 is decreased from 99% to 95%. So in other words, let's pretend like we keep everything the same. We keep the same sample size from before, 758. The only thing we're changing about problem 4 is we're lowering our confidence to 95%. So question, what is the new margin of error? So remember, the margin of error is the critical z-score times p hat 1 minus p hat divided by n, right? So what we're going to do now is we're going to do the same as before, right? We had this margin of error calculation, except now instead of 2.576, we're going to put the critical z-score for a 95% confidence interval, which recall is actually 1.96, right? So we're going to replace the 2.576 with 1.976. Or sorry, 1.96. And let's see what we get. So we're keeping everything else the same. So I'm going to go ahead and do this on my calculator as well. And let's see what we get. So I got 0.029. So how does that compare to the old margin of error? Remember, the old margin of error was 0.038, so it still made it smaller, didn't it? The new margin of error is smaller. So what did we learn from this? We learned that if we decrease the level of confidence, the confidence interval gets what? Narrower, right? So the confidence interval gets narrower. Okay. It does say explain your answer, so I will say that it gets multiplied by a smaller number. What do I mean by this? Well, I want you to look above at my formula for my margin of error. You notice that this is being multiplied by ZC. So what this is saying is that if I were to take my ZC right here and make it smaller, then of course this whole thing would get smaller because I'm multiplying everything by ZC, right? So if I make that guy smaller, then the whole thing gets smaller. So let's take a step back here for a second, okay? We now know of two ways to make our margin of error smaller. One of them is to increase the sample size. Another one is to lower our confidence. Okay. So let's read this question. It says, in questions 5 and 6, we learned that there are two ways to decrease the margin of error in an estimate. We can increase the sample size or decrease the confidence level. What is the best way to lower the margin of error? Well, do we really want to give up confidence? I mean, yeah, it's nice to say that something is more precise, but not if we have to be less confident about it, right? So the trick is if we want to get a tighter margin of error without giving up any confidence, the best way is to increase the sample size. So I'll say increasing the sample size is the best way to decrease the margin of error. Okay, so this is an important fact. You do need to know this for the future, but don't worry, we will revisit it quite a bit in these future lessons, okay? So you need to know there are two things that influence the size of the margin of error and the resulting width of the confidence interval. Increasing the sample size decreases the margin of error and makes the confidence interval narrower. Decreasing the level of confidence decreases the margin of error and makes the confidence interval narrower. So both of these things do. This next sentence is the most important part though, okay? Small margins of errors are nice, but not at the expense of the confidence level. As a general rule, the best way to decrease the margin of error is to increase the sample size. Okay, guys? So the code word for this lesson is alien. Okay? So that's what you're going to submit. Thank you very much for watching, everyone. I hope this video